All right, welcome back to calculus. So now we approach section 6.8. Now, if you look in 6.7, there was a sort of an alternative approach to introducing the idea of the transcendental number e and e to the x and the natural log of x. So that's good, although I have approached that in different ways earlier. So now we're going to apply the exponential and logarithmic functions in 6.7, exponential growth and exponential decay. Now, these are, again, some of the most important applications of calculus in natural sciences and actually in social sciences as well, because as you will see, many things grow or decay exponentially. And so let's take a look at this, section 6.8. All right, so I am going to talk about 6.8 rather lightly. It's about exponential growth and decay, and you may have actually studied this in a class before calculus, like in pre-calculus, because certainly this is accessible without knowing a lot of calculus. But before we get into that, right, let me just mention casually or informally about what the author of this OpenStax book did in section 6.7. All right. So, I mentioned, right, so here's what we did. All right. What I did in explaining the exponential and logarithmic functions is this. First, I defined what E was, okay? And I said E is the limit of this quantity 1 plus 1 minus 1 over n to the nth power as n approaches infinity. Now, this is the traditional definition of E. There are many different ways actually to define E, as the author does here too, but I define E as this limit. Now, this comes sort of naturally when you do compound interest in finance, of all places, finance, not science or mathematics or computer science, but in finance, when you start doing compounding interest in the continuous compounding way, then this is naturally, this arises naturally as a limit number. And it's surprising that this limit actually exists, right? And it turns out to be a very strange number. And so that is that's one way to define this. And remember what I said, this number here wants to become closer and closer to 1, wants to stay small, but this tries to pull this to bigger and bigger numbers. So this is a classic Peter Pan, right? Inside you want to stay small, but the outside world force tries to make this bigger and bigger, and it comes to a compromise to a rather small number. It's an intricate balance, but the compromise is it settles at 2.718, irrational number, transcendental number, which we know as E. And then we defined a log based on E, and we called it natural logarithm. So it's the log based on E of x, right? And log is just the inverse function of that. So when I say, log of x is y, basically all I'm saying is e to the y is equal to x. All right, so that's how we define the natural log. And then we calculate it based on this definition and this, and the definition of a derivative. The derivative is the limit as h approaches 0 of the difference quotient. And we found that the derivative of the natural log function turns out to be 1 over x. We took the limits, and this, I think, was a very beautiful way to derive the derivative of a natural log function. And it's beautiful because there is no additional thinking here. If you took any other base for this logarithm, you would have to have log of natural log of that number, the base number, almost like the penalty for using a unnatural base for the logarithm. But if you take the log base e, you get 1 over x, the very simple reciprocal function as your derivative. And then based on that and implicit differentiation, we found d dx of e to the x was itself another very, very elegant and a beautiful mathematical equation here. This is one of the most awesome things you see in calculus, right? And then we immediately we can figure out based on this that the integral of e to the x is e to the x plus c, right? And then the integral of dx over x is the natural log of, and we had to do a little work when x is negative, but this turns out to be the natural log of the absolute value of c. So this is the approach we took as we derived these elegant and extremely wonderful ideas or theorems. Okay, so what they do in the book in 6.7 is, and I must say, this sounds great, but from the purely mathematical standpoint, maybe it is not the best way to approach that. There are some issues, technical issues when you try to rigorously prove all of these. I think this is a great idea, and I am happy with it. But if you look at this alternative approach, which is very counterintuitive, let me just explain that. If you don't understand this part, that is perfectly fine. But what they do, very unnaturally, is to define Ln of x not as a logarithm of anything, but Ln of x as the integral from 1 to x of the reciprocal function. So you have this reciprocal function, right? It's 1 over t, and you find the area between 1 and this point x, where x is a variable. And so if you define this area function to be Ln of x, not necessarily logarithms, okay, then of course ddx of Ln of x is 1 over x by the fundamental theorem of calculus, because the fundamental theorem of calculus says this integral, the derivative of that, has to be 1 over t or 1 over x in this situation. Okay, that's really by definition, well, by the theorem, because this theorem says the derivative of this integral, the area function, has to be the integrand itself, which is the reciprocal function. All right, and then they show through sort of a pretty easy to calculate way dx over x. All right, so this is going to be, again, this will be the opposite way. You take the integral of this, and you should get the natural log, but you also get the natural log of the negative side, absolute value of x, and so that you can get that. Right? Then they show, now remember, this was not defined as a logarithm of anything. This was just the area function. Then they show that Ln1 is equal to 0. Now that's easy because you just get one, the area from 1 to 1. And then they show something like the Ln of AB is Ln of A plus Ln of B. It's not a trivial thing to prove these things, because remember, you don't know that this is any kind of a logarithm. And then you can show that Ln of A divided by B is Ln of A minus Ln of B. You can also show that Ln of A to the kth power is k times Ln of A, and so on. Okay, so this shows that this Ln behaves like a logarithm. Remember, we didn't define Ln as log in this alternative way of discussing this. So once you show that this area function behaves like a logarithm, then you can start looking for the base. What is the base of this logarithm? So you let E be the base of this area function, which we call Ln of x, which now we can see that it acts like a logarithm. It doesn't say it is a logarithm, but it behaves like that. So then find E to be the base, okay? And we define E to be in such a way that Ln of E is equal to 1. And then you do all sorts of other things that we did before. Okay, again, this is very counterintuitive. I don't think it's very productive, actually, but some people insist that this is the better way to do this, and I am fine with it, but I think this is much better. This is also more elegant, in my opinion. All right, so with that, let's just go to again, very quickly discuss what we have in section 6.8. So this is exponential growth and decay. And this introduces you to a big area of mathematics. In fact, a huge application area of calculus called differential equations. Right? So you have this quantity Q, which changes with respect to time. Right? Let's say it grows by 3%. See, you can say a lot of things in this world grows by certain percentages, okay? So for instance, the money you invest into an account grows by a certain percentage. The population grows by certain percentage. And when you say that the population grows by a certain percentage, it grows to, it doesn't grow, well, it grows by 3% annually, let's say. And then the following year, it grows by 3% of the new number. And then the following year, it grows by 3% of that previous number, right? So the growth is going to be exponential. And, or you can say something decays by 10% or something. All right, let's say you start with $100. If it decays or depreciates by 10%, the following year, it's going to be 90, okay? But the following year, you lose 10% of 90, so that would be 9 subtracted from 90, it's 89, right? And so now the amount of decreases actually shrinks. And so this will be an exponential decay that's going to look more like this. It's not a straight line thing, okay? And so what is involved in here? Here's what's happening. When you say the growth is by a certain percentage of the current number, right? What we have is, let's say Y increases in direct proportion. Like when you say 3% of something, it's direct proportion to Y. That's what, in the language, when you say the constant percentage growth, what you're saying is that quantity is growing at the rate which is directly proportional to Y. All right, so that means dy over Y. Okay, so that is the growth rate, right? The instantaneous rate of change, dy over Y. I'm sorry, I should say dy over dt. Okay, that is the rate of the change of Y, the growth of Y with respect to time t is proportional to Y, because you're saying 3% of the proportion population or 3% of the price or whatever. So this is exactly what you have, okay? The rate of the change of Y, the rate of the growth of Y is directly proportional to its quantity at that moment. Okay, and at that moment, it constantly changes, right? The Y is constantly changing and it grows. And so as Y grows, the rate of change also grows. It gets faster and faster, thus the exponential growth. So what do we have here? I mean, this is also saying Y prime is KY. It's the same thing, right? All right. Now this is a what we call a differential equation. You have an equation that involves a derivative, okay? And we solve this. Now, the theory of differential equations is well established. And the way we do this, and typically we write this as dy is equal to ky dt. You just multiply both sides by dt, okay? And that's fine too. You can also separate y's and the independent variables like this, okay? And then you integrate both sides. You don't actually have to understand each step of this. This is something that you will be doing in more advanced class differential equations. Integrate both sides. And so in a sense, you're going integral of dy over y is equal to k times integral of dt. And you get natural log of y here, right? Is equal to kt plus C, let's call it C naught because you'll see why. Okay. Now, it's actually absolute of y, but we assume that y is some quantity like the population or something that is positive. So we just take the absolute value sign removed. So it's a log of y is this. Now, then you can do e to both sides like this. Okay, now it looks so bad. I'm not going to do that. Exponentiate both sides. And you get y is equal to e to the kt plus c naught, which is e to the kt times e to the c naught. Okay, let's call this a constant, just c. Okay, so this will be c times e to the kt. All right, so what happens, this whole thing, what I just mentioned in the last 2 minutes is basically saying anytime the rate of change is proportional to the quantity itself, the current quantity. Okay, anytime the rate of change is proportional to the current quantity, with the k as the constant of proportionality, that gives rise to the answer y is equal to c, the constant, times e to the kt. This is exponential, right? In other words, anytime the rate of change is in proportion to the current value, the quantity grows exponentially. Right? If k is negative, it decays exponentially. Right? So this describes exponential growth as well as exponential decay. Now, if t is equal to 0, that's going to give you the initial population or initial value, and that's going to be c times e to the 0, which is c. All right, so c is the initial value. Typically, it's written as y naught. Okay, so that will be y at time 0. So here is the summary of everything I just said here. Exponential change is of the form y of t is equal to the initial value, y naught, times e to the kt. Right? Every exponential growth or decay can be described this way. This is the initial value, okay? And k is the constant, which we need to find depending on how fast or how slow the rate is. Now, if k is positive, sorry, k cannot be 0 because then things don't change. If k is positive, then it's called exponential growth. If k is negative, you'll see the numbers increasing, and that's the exponential decay. All right, so exponential decay and exponential growth both are growth or decay by percentage, a fixed percentage, and that percentage determines what that value k is. All right, and so this is a very important thing which can be applied, as I said, to many, many things. The consumer price index seems to grow exponentially. The world population, the population of any kind of species or number of bacteria, for instance, seems to grow exponentially unless there is some sort of an inhibitor that is slowing the process down. Okay, radioactive substances decay exponentially until they get to a certain point where there's no more decay. All right, so this is a equation that governs or rules so many different phenomena in the society or in the scientific world in which we live. Okay, so here's an example. Let's talk about a number of bacteria or virus, okay, or anything that can cause health issues. Okay, so the number of bacteria, let's say the population is determined at t. Okay, and so people have done, or scientists have made an observation. You start with 200 bacteria at time 0, and let's find out after 2 hours it became 2,000. Okay, bacteria grows exponentially, and they tend to grow pretty fast, just like viruses. All right, so based on these two, let's find P5. Can you do that? Okay, now you are given, well, we are assuming that the number of bacteria grows exponentially. Okay, so there's a constant rate, constant percentage. It's going to be a certain percentage per hour it's increasing. And in 2 hours, it's growing to be 10 times fast. That's quite fast, right? So the starting point for questions like this is always this formula, okay? Because exponential function or exponential growth always follows this equation. All right, so y is y naught times e to the kt. Y naught is 200 in this case. Remember, it's always the initial value. And the way to remember that is when t is equal to 0, y is y naught times 1, which is y naught, right? Okay, so this will be y is equal to, I guess we can call it, did I call it p? Yeah, so let's just call it p. Yeah, that's fine. All right, so p of t is actually 200 times e to the kt. All right, we don't know what k is yet, and that's why we need this other piece of information. P of 2, which is 200 times e to the k2 is 2000, right? So that means e to the 2k is 2000 divided by 200, that's 10. And so that means the natural log, well, okay, 2k, taking the natural log of both sides, is going to be ln of 10. And so k is 1/2 ln of 10. And then that, you can calculate this on your calculator. And by the way, this happened to be ln of the square root of 10. Remember, the 1/2 can go to the back. You don't have to know that. But k, if you calculate this on your calculator, is going to be 1.15129. All right, so now we have a nice equation of p. P of t is actually 200 times e to the 1.15129 blah, blah, blah t, okay? And this number is usually not a very nice number. It's usually an irrational number because the natural log function is involved in this. I should just give you a little side note or a footnote, okay? You could also write this if you don't like to, well, if you rather use something else besides e, you could do that, all right? So this is p of t is equal to 200 times e to what, right? E to this thing, right? That's the constant k. So this is e to the natural log of square root of 10 times t. If you want to do that, you could. And you know, e to the natural log of, those are inverses of each other. So this is another way to write the same function, if you would like, okay? So this turns out to be 200 times approximately 3.162277778 to the tth power. And that is one way to write the same kind of function. See, there's nothing magic, well, I shouldn't say that, nothing magical about e. The point is, for any exponential growth, you don't have to actually use e. Okay, you could use something like this. Now, this actually tells you that each hour lapsed, the number of bacteria grows to become about 3 times as much as an hour before. So every hour passed, you will have 3.16 times as many bacteria as an hour ago. So that number is actually pretty significant. But of course, that number is the same as this number, you know, if you want to find that number. So anyway, all right, so the answer to this question, I think the question was how many bacteria you will have after 5 hours. So you just plug in 5 and you get 200 times e to the 1.15129, blah, 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 times 5, and you will get your answer. And I have the answer somewhere. That's about 63,246 bacteria. Sorry, bacteria. That's the plural of the word bacterium. Okay. Now, if you plug that t is equal to 5 into this equation, you will get, of course, exactly the same number, right? And so here's one fact. Anytime you have exponential growth, that's based on a certain fixed percentage, okay? Percentage growth, and that's actually this number -1. So it's what, 216. This minus 1 is 2.16, right? So it's a 216.2278% population growth per hour. That's the fact. And so anytime you have this exponential thing, exponential growth, there is a fixed doubling time. If the equation describes a decay function, there will be a half-time, or half-life is what they call that in chemistry, for instance, for decaying objects. Okay, and so let's see, y is equal to y naught e to the kt, right? Okay, if you want a doubling time, you want this to be 2 y naught, right? Because this is exactly the double amount of the initial value. And so, of course, you can just cancel this. If you want, I'm trying to find the doubling time, or doubling time for any kind of exponential growth, right? So this basically says kt is natural log of 2. So the half time, or the doubling time, is always found by a 1 over k times ln of 2. And this will give you the doubling time given the constant k. Okay, in the above example, if you try to find the doubling time here, it's 1 over that number, which is what? K was 1.15129 something, right? Remember? Yeah, that K. If you plug that number in the denominator and multiply by log 2, you will get approximately 0.602 hours. 0.6 hours, that's what, about 36 minutes, because 0.1 hour is 6 minutes. Around 36 minutes. So this is saying, okay, with this given information, every hour, no, I'm sorry, every 36 minutes, the number of bacteria doubles, okay, every 36 minutes. So if you start with 200, 36 minutes later, you'll have 400. And 36 minutes after that, it'll be 800. It's going to be doubling of the double amount, and so on. And exponential functions grow that way. It grows so fast that it is hard to believe. Okay? So here's an example. This is one of my favorite examples that I share in another class for non-science students as well. Okay, so if you have t to the t, let's say t is measured in days. Now, what kind of a function is this? It's a function that doubles every day. Okay, so a scenario you can imagine is like if you have a magic dollar bill, you find a $1 bill one day, and it just doubles for some reason. The next day you have $2 bills, the next day you have $4 bills. Okay, so p of 0 is of course 1, and p of 1 is 2. P of 2 is 2 squared, which is 4. So after 2 days, okay, on the initial day you have $1 bill, next day you have $2 bills, next day you have $4 bills, next day you have $8 bills, which you can't really do much with, okay? But if you wait for 10 days, this becomes $1,024. If you wait for 20 days, then 2 to the 20th, which is about $1.04 million. Are you serious? Yes, if you wait for 30 days, you'll have 2 to the 30 number of $1 bills, which turns out to be about $1.07 billion. Okay, let's stop after 33 days, because here you'll have 8.6 billion. All right, now imagine this is the number of, what do you want this to be? Number of people in a certain group or something. And because this group, a new, trend setting group, maybe the number of Instagram users or something. Let's say it really doubles every day. You start on day 0, you have 1 user of some app, social network or something. And then the next day you have 2, and next day you have 4, and next day you have 8. Okay, after 10 days, you have 1,000 people using that app. Okay, but if this doubling continues, truly, if the doubling continues and it doubles every day, this is hard to believe, okay? But after 30 days, after like a month, you have like 1.07 billion people. And if you wait for 3 more days, by the end of 33 days, you'll have 8.6 billion users. That's like the entire world, you know? So this is crazy, okay? But that's the power of compounding. That's the power of exponential growth. And you do not underestimate the power of compounding growth or the power of exponential growth. All right, I'm going to do one more example in the second segment of my video lesson for section 6.8, where we will talk about actual numbers of COVID-19 cases in 2020.